Okay, so if we are all ready, we are going to start the second session of this new online seminar. It is a pleasure to welcome here Enrico Valdinocci from the University of Western Australia. And he will talk about a topic that in principle seems really on the bridge between analysis and geometry. That's the idea. And the title of the talk is It Happens, but only as the root of 1 minus s. So please.
Thanks a lot. Thanks a lot, Esther. So it's a pleasure for me to be here, at least virtually. And please feel free to stop me, interrupt me, and ask any question anytime. So the talk will be divided into two parts. First, I will recall what a non-local minimal surface is, and focus especially on the concept of minimizers. The second part of the talk is in a sense more general because we will consider critical points that are not necessarily minimizers, though that is perhaps too ambitious. So at some point we will focus specifically on stable critical points. So critical points that are not necessarily minimizers, but still the second variation of the energy functional, so in this case of the fractional perimeter, is non-negative. And we will understand also the meaning of the title, why it happens, but why, fortunately, it happens only as the root of 1 minus s. S will be my fractional parameter in a sense that I'm going to discuss now. So for me, S is a parameter between 0 and 1, and I consider what Caffarelli, Roggioff, and Savin denoted the S perimeter of a set E in omega. Now, the definition is kind of ugly, but roughly speaking, it wants to consider all the possible interactions between a set E and the complement of E, taking into account only the interactions in which the container omega is involved. So there are many motivations for this fractional perimeter. You may think it comes from, for instance, long-range phase coexistence models. So for genuinely long-range Allen-Kahn equations in which you have the particle interaction described by the fractional Laplacian when the order of the operator is less than 1, basically at a large scale, the picture that you see is the one described by this S perimeter. And so the minimizers of this S perimeter are called S minimal sets or S minimal surfaces, with a little bit of abuse of notation in the sense that one thinks that the boundary of this set is a surface. But among the motivation, let me show this one that was described in a paper with Eleonora Cinti and Joachim Serra a while ago. So suppose that you want to compute the perimeter of a square. This seems a triviality, but you want to do it with a computer because nowadays we are too lazy, we don't do calculations anymore. Artificial intelligence will tell me what is the perimeter of a square. Okay, and then your computer is very expensive. It has a screen, it has pixels. The pixels are very small because the resolution of the screen is very high. So the idea is that your pixels are of side epsilon, your square is of side 1. So we know, after all, that the perimeter of the square must be 4. The issue, however, is that there is a rotation, say, of 45 degrees between the pixels and the square. And now the computer makes a small numerical error because instead of considering the square as it is, it has to digitalize the image using the pixel, and so it replaces a segment with the sawtooth curve. Well, once the perimeter is considered for the digitalized image, the result that you get is 4 square root of 2 instead of 4. So not only is significantly larger than the correct result, but it's independent of epsilon. This means that no matter how expensive your computer is, because you pay more to increase the definition of the image, well, the error will remain the same. Instead, the approximation with non-local perimeters is more robust, because the error that you produce with the non-local perimeter comes, well, of course, from the fact that you replace a segment with the sawtooth form. But the idea is that you have the error coming from 1 over epsilon pixels, or order of 1 over epsilon pixels, that are the pixels that intersect the sides of the original square. Now, the S perimeter of each pixel is epsilon to the 2 minus S. This is just because the kernel, the interaction kernel of the S perimeter scales in this form. But then the total error is the product between 1 over epsilon, the number of pixels, and epsilon to the 2 minus S, which is the error produced in each pixel. And now the error is epsilon to the 1 minus S. This is good news because you still make an error because you digitalize a picture, so there is a bit of numerical error, but this error now tends to 0 when epsilon is more. So now you can spend more money and buy a better computer, and you will get a more accurate answer from that. Now, the paper by Caffelli, Rojoffre, and Savin proves many things, like an existence theorem, a maximum principle, a regularity result, and an equation that we will discuss later on. So basically, if you have an S minimal set E, and you have a point on the boundary, for instance, the origin, then you have an integral equation satisfied by the characteristic function. And we will go back to this equation later on, but basically for me, this object here in green plays the role of a non-local mean curvature. The analogy is that minimizers, or more general critical points of the perimeter, satisfy a 0 mean curvature equation. So since this may be seen as the Euler-Lagrange equation for the S perimeter functional, the left-hand side of this equation plays the role of a non-local mean curvature. In terms of regularity, so far, not much is known. So up to now, we know that there is regularity in dimension 2. This was a result obtained a while ago with Ovidiu Savin. And consider that it's already non-trivial, because while in the classical case, dimension 2 only gives you segment, so you know regularity just by inspection, just by solving the equation. For non-local minimal sets, the situation is more complicated. You cannot explicitly solve the equation, not even in dimension 2. So in principle, it's not obvious that the corresponding solutions are regular. And the idea, so why the proof is not completely obvious? Well, consider that in the classical case, if you have a corner like this one, you may say, oh, this is not going to be minimal because I cut the corner and I reduce the perimeter, I reduce the length. But for the non-local analog, you cannot just cut and say that you have decreased energy, because basically every point interacts with every point. And so it's very difficult to compute the difference of the interactions in general. Also, this is just an example, but we have to rule out all possible types of singularities. There is, however, another approach in the classical case that can be extended to the non-local scenario, that is using a flow to deform your initial candidate. So basically, if your initial candidate looks like that, you may think, okay, I take a point here on this side, then I take a smooth diffeomorphism that sends the origin to this point, say 1, 1, and I cut off this smooth diffeomorphism far away at distance r, or r plus 1. So basically, you change your initial corner into a slightly more open corner. And in the classical case, you gain doing this because the side of the hypotenusa is now the root of r squared plus 1, while the two sides are 1 and r. And so you can see that the difference between the gain and the loss between the two competitors is 1 plus r minus the root of r squared plus 1, which is going to be positive if r is large enough. Now, this is, this is just a picture, okay? But the fact is that the picture can be extended and a rigorous proof can be made. But just let me make a remark about this picture. So this picture has somehow a simplifying assumption, because I'm moving the original corner in the right direction in order to lower the energy. Now, strictly speaking, in general, I don't know what this direction is. So if I want to transform this picture into a real proof, I have to somehow average between, say, the best and the worst possibility. So I will not move the corner just in one direction because I don't know which one is the right one. So I will move in one direction and in the opposite one. And I will average out. Now, the minimality implies that this second order incremental quotient has a sign. But then when you do this kind of operations, then you realize that this is a natural notion to look at. So the minimality implies the positivity of a second order incremental quotient. And this is exactly the part that I will retake in the second part, in the second chunk of my talk, in which I will discuss stable critical points. So let me skip a bit some details. Just for consistency, if you wonder what is the relation between the S perimeter that I'm treating here and the classical perimeter, well, up to normalizing constants, the S perimeter will converge to the classical perimeter as S goes to 1. And this is important also in terms of regularity, because the only other regularity result known so far is a paper with Luis Caffarelli that says that if S is close to 1, non-local minimal surfaces are as regular as classical minimal surfaces. So this is pretty much the state of the art. So we know regularity in dimension 2, we know regularity up to dimension 7, provided that S is close to 1. But we don't have counterexamples. And the other cases, I would say, are quite open. I think that understanding, proving or disproving regularity of non-local minimal surfaces is one of the major problems in the current research. And an interesting feature of the non-local minimal surfaces is that they present a surprisingly different behavior with respect to their classical counterpart. So this is something that we discovered with Serena Di Piero and Ovidiu Savin, and we call this behavior stickiness. There is a simple example that we can show by a picture to understand what stickiness is. In a sense, it corresponds to a boundary discontinuity that forces somehow the minimal set, the S minimal set, to adhere, to stick at the boundary of the domain. So this is a very general phenomenon. It occurs in many circumstances, but I think that the picture I'm going to show is perhaps the most striking one. So consider now your reference set to be the vertical slab, -1, 1 times r, and take as external datum a half plane. Well, now Caffarelli, Rogoff, and Savin proved the maximum principle, according to which if the external datum is a half plane, then the corresponding S minimal set is exactly the half plane. So you start with a half plane outside, you get a half plane between -1 and 1. Okay, that's not surprising. It's not trivial because to prove it, you have to go through the maximum principles, so the Euler-Lagrange equation in the viscosity sense. So without extra assumptions, this is already a non-trivial theorem, saying that if you are a plane outside, you are a plane inside, is already something that requires a careful proof in general. But this comes from Caffarelli, Rogoff, and Savin. Now suppose that you perturb a bit your datum outside, so you add a little bump. Well, then what happens is that there is a non-local interaction between these little bumps. Say I'm putting here two symmetric bumps on both sides, but I mean this is just to make a nice picture. The situation is much more general than this. But then basically what happens is that these bumps force the S minimal set to lift up. So the center of the picture will go up a little bit. Well, by maximum principle, you cannot overcome, you cannot surpass the height of the bumps, but still you bend up a bit in the center. But what is more surprising is that on the boundary of the domain, you have a discontinuity. So your function will be smooth inside up to the boundary, but then there will be a jump with respect to the external datum. So if you start like this, then you add the bump, you add the bump, and you have a situation like this. So you will develop a vertical tangency here and a boundary discontinuity. And I mean, there are many examples you can quantify. So basically, if you can quantify the discontinuity, so if the bump is of order delta, and delta is small, say, then the jump is of order delta to the beta. And beta is somewhat explicit. So this is a purely non-local phenomenon because it has no counterpart for classical minimal surfaces. So classical minimal surfaces for convex domains tend to cross the domain transversally. But this is instead not the case. And you have boundary continuity also for convex domains. You can prove it using planar barriers. But for non-local minimal surfaces, the situation is completely different in a sense. And okay, the proof of this phenomenon is in this case not easy. You have to cook up a suitable barrier that is basically obtained by the infinite iteration of power-like functions and straight lines. And then I'm not going into the details, but stickiness is a general phenomenon. So you can also have stickiness to the side of a box. So if you have so your box and you prescribe data outside that are two half planes at a different height, one on the left and one on the right, well, the corresponding non-local minimal set will have vertical discontinuities at the boundary of the domain. So it's not going to cross like a straight line, like a segment joining the 2 points. It will stick vertically and then make an interpolation between the 2 jumps. Or for small values of the fractional parameters, for instance, if you take a quadrant or a cone at infinity with an angle that is not pi, say, so for instance, I take a quadrant, which is a 90 degrees angle as the outside data, then when I send S to 0, basically the corresponding S minimal surface will get closer and closer to the boundary of the ball, but will stick completely at the boundary to the boundary of the ball for some small but non-zero S. So basically you have an example in which you put a non-trivial datum outside, and the corresponding S minimal surface occupies the whole domain. And this again, I think it's kind of surprising and thought-provoking. Now let me go now to the second part of the talk, in which I look for critical points that are not necessarily stable. So basically, these are just stationary solutions of the fractional mean curvature equation that I was introducing and discussing before. Now, as I was mentioning, studying all possible critical points may be too challenging and may not even be the point of many applications in practice, because for all energy functionals of interest, actually in nature, we don't see so many critical points. So even for classical minimal surfaces, you have plenty of galleries of images of beautiful and complicated surfaces of zero mean curvature, but then in nature, you don't really see them. And so the fact is that many of these critical points appear to be unstable, so small perturbations can easily destroy them. And so we focus now on stable critical points of the fractional perimeter, also called stable non-local minimal surfaces. And this is a trend of investigation that was initiated by some papers by Eleonora Cinti, Joachim Serra, and myself, Cabré, Cinti, and Serra, and so on. And now there is a very active group in Zurich led by Joachim, which is doing great things on this topic. And yes, so as I was saying, stability is an energy requirement because it corresponds to non-negative second variation of the fractional perimeter function. So to be a stationary solution, we want the first variation to be 0. This would correspond to the Euler-Lagrange equation. But then we want the functional to have somehow, maybe not a minimum, but still develop a non-negative second variation at this critical point. Now, as I was anticipating in the title, when you do complicated things, shit can happen, and that's not a good thing in general, right? What I mean by shit? Well, for instance, even in the classical case, what I'm drawing here is a catenoid. Now, the catenoid is a nice surface with zero mean curvature. Now, the unpleasant situation provided by the catenoid is that since zero mean curvature is a scale invariant concept, I can look at the catenoid at a larger scale, so blow down, and obtain another catenoid, which is still zero mean curvature. So this is the blue one. And I can scale again. So I find now the green one. What's wrong with that is that the catenoid grows only logarithmically at infinity. So when I do a homogeneous blowdown, basically the sheets at infinity get closer and closer, and so they produce a picture of this type. So somewhat in the limit, what I was perceiving for a finite scale as the two folds of the same surface, well, if I keep scaling further and further, these sheets will collapse one onto the other. And so somehow in the limit, I lose the geometry of the catenoid, I lose the multiplicity at infinity of the catenoid, and instead I get an algebraic multiplicity of the limit plane. So unless you really like this kind of pathologies, I mean, for people like me, this is a bad situation because there is a loss of structural information. So the limit catenoid is actually just two planes, one over the other. And so somehow we are trading the geometric complexity of the initial catenoid for algebraic multiplicity, which in a sense is more difficult to handle, in my opinion, because you lose intuition and geometric interpretation, and you have to rely on currents, variables, or more abstract objects of that sort. So this is maybe not a nice example because the catenoid is finite with Morse index, but it's not stable. So you may say, oh, but these pathologies only occur for unstable minimal surfaces. But that's not the case. And the reason is, I think, purely geometric. So what happens is that in order to have stability of a critical point, it is sufficient to find an epsilon of room where to put perturbations that increase the functional. So for instance, what I'm drawing now is a plane. Now a plane is a minimizer, so it's a stable point of the classical perimeter. But let me show that a plane is a minimizer. Well, you know what? I can just take any portion of the surface of the plane and modify with a normal perturbation. So of course I have increased the surface, and so this proves that the plane is a minimal surface. But unfortunately, this idea works also for a large number of planes. Now, if I have a large number of planes, that is not anymore a local minimizer of the energy, because if I take a very large ball, I can get rid of all these parallel sheets and just take a small portion of the sphere at the boundary. I would decrease the area. But the fact is that the same proof that I was discussing above works for a configuration of parallel planes, because I can make a small perturbation near one of these sheets, and I would increase a little bit the surface, and so therefore the energy. So this proves that this kind of configurations are stable critical points of the classical perimeter. Because after all, it's not necessarily to increase energy for all possible perturbations. Since the second derivative is something that you only do for small increments, it suffices to have space in one direction and have a small bump. So if I have a little bit of space, very little space between two parallel planes, I can still play this game, and I will increase a little bit the energy. So this proves that sheet can happen for classical minimal surfaces, for classical stable surfaces of zero mean curvature. Now, there are a number of situations in which prominent people have somehow ruled out these unpleasant configurations, but usually you have to assume something, for instance, connectedness. And this is a case, however, in which the fractional theory is somehow more robust than the classical one. So we have already experienced this in the first example of the computer computing the perimeter of the square, right? The classical approach was unsuccessful because it was too stiff, too rigid. Instead, the non-local one, since it comprises the global picture, the non-local one is more flexible, stronger, more robust. And you can see this, for instance, from this theorem that I had with Eleonora and Joachim. So the theorem says that, so if E is a stable critical point of the S fractional perimeter in a ball, say the ball of radius 2r, then the perimeter in the ball of radius r goes like r to the n minus 1, and the S perimeter goes like r to the n minus s. Now this is okay, maybe doesn't sound too striking for you, but I think it's instead a very powerful result because it tells us many things. So first of all, there is no dimension assumption on this theorem. So this is somehow the only regularity theorem for non-local minimal surfaces that it's valid in every dimension. And well, and here you don't even need minimality. Stable is enough. And it's a regularity result because you are saying that that the stable critical points satisfy somehow a BV estimate. They have finite perimeter, and actually they have a perimeter with the right concept of scaling. So you may think, oh, I would like to say that the surface is smooth. Well, in every dimension, that is not only unknown, but probably not even true, right? But still, the fact that you can have a small regularity improvement because somehow the S perimeter is a weaker notion than the perimeter. So having a perimeter bound is something that you cannot just extract from energy considerations, right? So it's a regularity result that is valid in every dimension. But more than that, for me, it's a result that suggests that sheets should be naturally reduced in the non-local case. Because, so for instance, take a large ball and suppose that at infinity, your datum has many ends. So it's like an octopus or a millipus with 8 or maybe 1,000 legs at infinity. Now, what the previous theorem tells you, that when you get closer to the origin, the number of ends that you can have is not going to be arbitrarily large because it's bounded by a constant. So basically, when you get closer and closer to the origin, well, all these ends must either die or merge between each other. So maybe this dies here or merge with the next one, then it gets closer and closer. So something survives, but not too many. Okay, and this is again something specific for the non-local scenario. So, for instance, it's telling you that if you have many parallel planes at infinity, well, if they are too many, well, they have to merge somehow. And yes, so there is an interesting example exactly of this form, looking at parallel planes, that was pointed out by Cabré, Cinti, and Serra. So when I say that the non-local world behaves better, well, of course, we cannot ask too much. The constant appearing here depends on the fractional parameter s, and it degenerates when s goes to 1, which is unavoidable because you cannot expect to rule out arbitrarily thin sheets in the classical case. But okay, you can give bounds on that. So there is this result of Cabré, Cinti, and Serra, saying that if you have infinitely many planes in the non-local setting, well, infinitely many planes at the same distance are always zero non-local minimal curvature, just by symmetry. However, if you want these planes to provide a stable critical point, then the distance has to be at least the root of 1 minus s. So this is important because it's suggesting that, yes, sheet can happen, but at least when you have parallel planes, they cannot get too close together. So you have a lower bound on the sheeting phenomenon. And this is exactly the starting point of the result I'm going to describe now. This was obtained with Serena Di Piero, with Ardi Chan, Serena Di Piero, and Joachim Serra. And so the main questions that you have after these examples is that can one obtain regularity bounds that are robust as s goes to 1? So can you say that maybe, okay, you have many sheets, but the sheets remain somehow regular? And the regularity remains uniform when you approach the classical case. Can you obtain optimal bounds for sheet separation? So we know, for instance, that planes, by the example of Cabré, Cinti, Serra, that planes have to be separated by a distance like the root of 1 minus s. What can we say in general? Okay, and so this is the paper we have with Hardy, Serena, and Joachim. And we focus on the case of stable critical points of the S perimeter in R3, or maybe in R4 if they have conical structure, because R4 with a conical structure, you can quotient out one dimension basically, because you argue at the level of the sphere. But just for simplicity, let's think about two-dimensional surfaces in R3 that are that have zero non-local mean curvature and are stable with respect to the S perimeter functional. And now I will give you the theorem. The theorem is a bit complicated, But basically it says that. So suppose that you have this ball, say the ball of radius 1, and suppose that in this ball you have a large number, possibly very, very large number of sheets. So I'm drawing black and white, say that the set is the black and the complement of the set is the white. And so the sheets are the boundary, are the boundaries of these sets. Okay. And then you consider one of these sheets. And you say, I have this sheet that is gamma x. And then I want to take the normal direction of this sheet, and I want to check where the next sheet may occur. And then the optimal separation that we prove is that there is a distance bounded from below by the root of 1 minus s. So the example of Cabré, Cinti, and Serra is not just an example, is the prototypical situation. So any other configuration can be much more complicated, but still you maintain a lower bound, which is of the order of the root of 1 minus s. And also, the graph describing this sheet is smooth, it's C2 alpha, in a way that remains stable, that remains robust, with an estimate that remains robust as s goes to 1. So this is the theorem if you want. I mean, it's a bit long and not super easy to read, but this is what I was saying. So the sheet is described by a graph, say of a function g, which is C2 alpha locally, fine. But the important thing is that the C2 alpha norm is bounded by a constant. So the graphicality scale will degenerate because the sheets will collapse maybe one over the other when s goes to 1, because the root of 1 minus s goes to 0. Fine. But the description of every single layer remains nice and smooth. So the surface is locally C2 alpha with a bound that does not degenerate as s goes to 1. And the other thing that I was telling you is the optimal separation sheet. So if you look at the next layer, well, the next layer is separated at least by the root of 1 minus s. And maybe the last thing that I can mention is this. So in the classical case, the position of the layers is totally arbitrary. So when you consider parallel planes as stable classical minimal surfaces, stable classical critical points of the perimeter functional, well, there is no information possible about the position of these sheets. Even in the picture I was showing before, these sheets were put wherever I wanted. Now, instead, in the non-local case, you can somehow identify the position of the layers in the sense that the function g describing the sheets solve a Toda-type system that actually appeared in a paper by Davila Del Pino and Wei, which is something like this. So if you look at the rescale profiles, so we know that the graphs of the sheets can collapse with the root of 1 minus s. So if you rescale these graphs in order to remove this possible degeneracy, so you multiply everything by the inverse of the root of 1 minus s, Now, this G tilde obtained by this vertical rescaling, well, all these G tilde i's are functions that are separated by a distance of order 1. And as S goes to 1, they solve a local equation, which is somehow explicit. So you may think, oh, it's not so nice. Well, it's not that bad either, because the left-hand side is a Laplacian, fine. The right-hand side has a denominator. Well, it has a changing sign just because every time you go to the next layer, somehow the normals change orientation, because you go from an inner to an outer normal. So this is the reason for which you have a sign changing anytime you meet a layer. But I mean, the worrisome part would be the denominator, right? Because if you are pessimistic, you say, okay, this is a terrible equation, because the denominator becomes 0, it blows up, and then you can say nothing on the solution. It's actually not the case, exactly because the separation of the GI entails that the G tilde I are separated uniformly. And so the denominator is actually bounded from below and provides no problem. And so in particular for the flat set, this gives a balancing condition describing the height of these surfaces. Yes, I don't have time to go into the proof, but let me say that the proof is delicate because separation and regularity go together. So you would like to say, of course I'm regular because I'm separated enough that I can put some kind of elliptic estimates in my domain. But you don't know that you are separated enough. Vice versa, you would like to say, oh, I'm separated enough because I'm regular, and so I can describe my surface in a tubular neighborhood. But you don't know that you're regular yet. So it's a bit of a chicken and the egg problem. So the idea is that the proof is based on several steps. So you start with an optimal separation in what we call L minus 2. L minus 2 means that the inverse of the distance between sheets is in L2. Now, this doesn't sound too exciting because L2 you may think is a very weak estimate, but it allows you to decouple the S-mean curvature equation, because the S-mean curvature equation in this case has to take into account the interaction between a large number of layers. And this is almost impossible to deal with. But then if you have some optimal separation in L minus 2, you can only look at the next layer interaction, and all the other layers, you put them on the right-hand side as a perturbation. So that is useful because you can improve the optimal separation in L minus 2 using now the non-local elliptic regularity theory to obtain a C alpha right-hand side and then bootstrap in a sense. Okay, so maybe my time is essentially over. Let me see that there is an interesting yes, there is an interesting byproduct of this, saying that if E is a stable critical point of the S perimeter in Rn with n up to 4, then E is necessarily a Hall space. So this kind of estimates produce, not for free, but I mean, as a corollary, essentially much easier than all the rest, they produce the classification of stable critical cones of the S perimeter in R4. And so the moral of the story, the take-home message, is that studying non-local minimal surfaces typically quite hard because the questions involved are technical and not easy to handle. But sometimes it is worth the effort because on many occasions local minimal surfaces happen to enjoy, maybe miraculously, maybe not, because after all the difficulty provided by the integral equation is sometimes a benefit because the integral equation encodes the full geometry of the surface because every point interacts with every other point. So this sometimes produces stronger and more robust regularity properties than classical minimal surfaces. So this is what I wanted to say. So thanks a lot for the kind invitation and for being with me so far.
Thank you, Enrico, for the nice talk. So now time for questions. So somebody. Okay. El audio. Well, I have actually one. So you have advertised very well that, the elliptic theory pays off is to study fractional minimal surfaces. What about the parabolic one? It is also worth fractional mean curvature flow?
Yes, this is also something that people have been studying. I have some papers with Mariel Saez, Eleonora Cinti, Carlo Sinestrari. Yes, I think it's a very beautiful topic as well. For instance, just let me tell you a result with Carlo and Eleonora, which I think also draws the attention that the non-local world is somehow different than the classical one. So in the classical mean curvature flow, the planar case is regular. So if you start with a dumbbell in the planar case, maybe even draw a picture. So in the classical case, if you are in the plane, and you start with a dumbbell, well, the dumbbell will not produce a singularity because, well, roughly speaking, on the external side, you have positive mean curvature, well, positive curvature, so it will tend to shrink. But in the middle, you have negative, so you tend to expand. So what happens? Well, I don't know, but roughly speaking, you will go to a set of this form, and then you will shrink more or less to a ball. This is Grayson theorem, basically. Now, in dimension 3, however, the dumbbell will produce singularity because in dimension 3, well, the curvature here of the neck is going to change sign because it's an average between a negative curvature, which is, however, almost zero, right? Because there is a little bit of negative curvature here, but there is a lot of positive curvature on the other side. So the mean curvature here is positive, and so it will shrink fast to zero. Now, in the non-local world, you can have actually examples of singularities in dimension 2, because in dimension 2, the neck here already has positive mean curvature, just because if it's small enough, the presence of the complement of the set dominates the presence of the set itself. Of course, you have to do calculations, But basically, when you stare at the picture, you realize, oh, dimension 2 already has the property that the dumbbell for the classical case has in dimension 3. And so you can produce singularities of the geometric non-local mean curvature flow also in dimension 2. And there are also positive results like convergence to balls and things like this. But yeah, so I think that even the parabolic case, the evolutionary case of the geometric flow associated to non-local mean curvature is a very beautiful topic, not easy because you cannot take derivatives, right? It's a little bit less implicit. There are no knowns Wisken monotonicity formulas for this case. So many questions are open due to the lack of classical instruments.
Mm-hmm. Okay, thanks. Anything else? Okay, so if nobody says anything, so thank you a lot again for the nice talk, and